Hi, in this lecture video, I'll be discussing the chemical property of the alkyne functional group, and then we will then begin to talk about the first chemical reaction of alkynes, the acid and base reaction of alkynes. So first, we see that alkynes are electron-rich functional group because along the carbon-carbon triple bond, there's up to 6 pairs of electron in them. 2 of the pair would then be the sigma electron, or the electron that is used to form the sigma bond between the 2 carbon. And then in addition to that, there's also pi electrons that make up the 2 or the double bond that we see in the triple bond. And because the alkyne is an electron-rich functional group, therefore it can behave as a good nucleophile and a good base. Okay. And so here's an example of it again. And so this is another view of what the triple bond would be. The 6 pi electron all together in a cylinder in this along the carbon-carbon triple bond. And based on this electron potential map right here, then we can see that here is an electron-rich region in the alkyne. So therefore, this is the part right here that make the alkyne the nucleophilic and basic as well. And overall, we see that alkyne can undergo reactions that are very similar to alkene, but then there's still a few differences between these two functional groups. Okay, and so here are the overview of the different types of reaction that alkyne can undergo that we will be discussing here in this class. And so this is a big overview. We will go over this reaction later. And please notice that if we were to be looking at this name right here, then there's many of this reaction name right here that we have seen already in when we learn about the reaction of the alkene. But now there's some additional reaction that we have not seen yet. For example, this dissolved metal reduction right here, then this is one of the reactions that we have not seen in the alkene yet. So now, let's talk about the acid and base reaction of alkyne. So, and this is basically what makes the alkyne slightly different compared to the alkane and the alkene that we have seen already. So alkyne are more acidic than the alkene and the alkane, and therefore they can undergo acid and base reaction. If we were to compare the pKa's between alkyne, alkene, and alkane, then we can see that here in this case right here, alkene pKa's is about in the 50 range. Versus for alkene, then the pKa's will be in the 45 range. And now as for the alkyne, and this is referring to a terminal alkyne right here, because they have to have hydrogen on them in order for them to be acidic, right? If they are the internal alkyne, then we would not be seeing this acidic proton right here. But for the terminal alkyne, in which the triple bond has a hydrogen on it, and then the pKa of that hydrogen right here is about 45. So you can see a whole lot more acidic compared to the alkene and the alkane, and therefore they can undergo acid and base reaction. So the terminal hydrogen on the alkyne can be deprotonated by using a strong base. And by when we say the strong base here, then we are referring to a base in which its conjugate acid would have a pKa of 25 or higher in order to be able to deprotonate a terminal alkyne. And so let's say here that we have a base, and now this base right here is a strong base in which it conjugates acid has pKa of 25 or higher. Then this base will be able to come in and pick up this hydrogen right here as a proton, and this electron it then donated this carbon. So now we will be able to convert this alkyne into something that we call the alkane. And so here it would be the types of base that we would need to use in order to protonate the alkyne. So this base is right here. So here is the cutoff point for the alkyne. So here, anything above this line right here, above this line, would correspond to the base that will be able to deprotonate an alkyne. For example, hydride. Hydride will be is strong enough of a base that will be able to deprotonate the hydrogen on the alkyne. Because it conjugate acid, H2 had now pKa of 35. And then Here's another example right here. This is basically a very common reagent right here that we use to deprotonate a hydrogen of the alkyne. So this is called the sodium amide right here. And the reason why is that when we basically use this, then to pick up the proton from the alkyne, it conjugate acid the ammonia that has a pK of 35. So this is quite strong right here and will be able to do a very good job in deprotonating the alkyne hydrogen. And clearly we can also use the alkene as well, or as well. But now the alkoxide here would not be basic enough to deprotonate an alkyne. And the reason why is that the conjugate acid is only about 16 to 18. So please remember that in order to deprotonate the alkyne hydrogen, we need something with a conjugate acid with pK of 25 or greater. And so these are the two very common examples right here, with sodium azide being the most common one. And now let's try some of this example right here to see if you can determine whether a base would be strong enough to be able to deprotonate an terminal alkyne. So here in the alkyne right here, treated with different reagent. So will any of this reagent right here be able to deprotonate the terminal alkyne? So let's first example here, sodium hydride. So yes or no? And the answer is yes. Because sodium hydride, once this come in to pick up this hydrogen right here, it will be producing H2. And the pK of H2, as we have seen already, is about 35. So therefore, sodium hydride will be able to deprotonate the terminal alkyne. And second, sodium amide. So clearly the answer would then be yes. And here is N-butyllithium. So N-butyllithium is basically when we have this 1, 2, 3, 4 carbon long, and this is negative and this positive. So clearly the conjugate acid of this has pK in the 50 range. So clearly this will be a very strong base. So this is an overkill right here, but it will be able to deprotonate the alkyne very easily. And as for this one, this is sodium ethoxide, and its conjugate acid would then be an alcohol. And alcohol have pKa in about 16 to 18 range, so that would not be enough. So therefore, alkoxide or sodium alkoxide will not be able to deprotonate the terminal alkyne.